Hello, this is Luke from Group 2. This is our analysis and redesign of a vibrating bull feeder.
And I'm Kabir.
I'm Ian.
I'm Chloe.
I'm Spencer.
And I'm Gerardo.
So what is a vibrating bull feeder? A vibrating bull feeder is a tool used in industrial manufacturing environments to feed small parts one at a time in a specific orientation. The current market size is about $130 million. The average estimated cost of a single bull feeder is $1,000 with over 100,000 units produced per year.
The primary customer for a vibratory bull feeder is the assembly division of a manufacturing company who requires small parts for assembly, whereas the secondary customer for the vibrating bull feeder is the individual staff that works on the line and makes use of this bull feeder.
This is Ian, and I'll talk about our assembly CAD. Here on the left side, you can see the upper bull feed assembly. The top section is mainly comprised of the bull and the bull support, and the lower part of that is the bull support piece. On the right side is the lower bull assembly. From the bottom up is the fixed base supports and the fixed base. And then that connects to the upper bull with the electromagnets and the spring units. And the spring unit is shown in a breakdown on the right side.
Now we'll analyze the function of the product as it is unmodified. So the task function of the part is to feed the parts, and it makes use of some subfunctions to store and dispense the parts. It does this by accepting, containing the parts, and then moving the parts with a directed motion. And then for the comfort of the operator, it prevents jams, secures the assembly, and minimizes the vibration. There are two possible assembly sequences. The first on the left side is a simple linear assembly, starting with the base and then adding parts one at a time from bottom to top until you have a completed assembly. The second option on the right basically splits the assembly into two sub-assemblies. The lower one, which starts with the base and adds the electromagnet and the various mounts, and then the one on the right starts with the bull support and adds everything up to the bull, which are then combined at the end.
So in comparison of those two sequences, the linear sequence is really good at transferring and handling parts. You can install one at a time, nice and easy to keep track of. And locating parts, but it is a lot weaker in testing sub-assemblies because it's not assembled in sub-assemblies. So you have to take it back apart to test each one individually. For sequence 2, it's not as good as transferring and handling parts because it's a lot more work to keep track of things as they're in different spots all at once. It's a lot better at testing sub-assemblies and assembling in parallel because as each sub-assembly is completed, you can test it before assembling into the final product.
This is the function component mapping matrix. On the top, you can see the functives from the fast, and on the rows, you can see the parts from the assembly. As you can see, the bowl is the most important part as it beats a lot of functives, and then a lot of the parts are used to secure the assembly, which leads to ample redesigning.
This is our bill of materials. This is the first part. The second part is continued on the next slide. We included the name, quantity, material, and then manufacturing and assembly processes, as well as the material processing and assembly costs. And the total cost is shown on the next slide.
This is the quad chart classification with the bill materials and the function matrix. We decided the bowl main support structure, the bowl and the base will be the most important ones to redesign. And then the bowl support ring, the bowl support plate, the electromagnet mounts, the bowl support mounts will be the ones we'll be looking to eliminate.
So for our product family design, we have this functional differentiation table. Basically, it just shows which functives are the same for different customer groups and which ones are going to be different. So most of them are the same except for the direct motion and secure assembly functives. And this is our component commonality table, which shows which components are different among the different customers, I guess, and which ones are the same. Those are the platforms. So most of them are platforms except for the one module, which is the outfeed bracket.
As Spencer mentioned, the common interface for the primary and secondary customers is going to be the general bowl. However, the outfeed bracket might be different depending on the general purpose. For the primary customer, they require adjustability for large-scale manufacturing because they purchase these in bulk and may need to use the bowl feeder for various feeding products, whereas the individual workers who work on the line or the secondary customers don't necessarily need adjustability because they're only working with one specific subassembly. So here you can see the CAD models for the primary and secondary customer. The primary customer has an outfeed bracket that's more adjustable, whereas the secondary customer has that bracket adjusted to be integrated into the total bowl. This is a closer look at the primary customer feed bracket. You can see that there is a slot that you can adjust the alignment pin to ensure that everything is aligned correctly when it's output.
Great. For the product family diagram, it just shows the loose assembly process to keep assembly costs down between the different modules and different products of the family. So basically the base, the electromagnets, and the bowl all get assembled together, and then the differentiating part, the outfeed bracket, is put on right at the end. So that way you have to keep track of fewer differentiating products.
Thank you.